Okay, howdy. So I'd like to say this is the last lecture, but I might switch these around. I think there's some logical reasons to turn this into number 18. But for now, for me right now, it's lesson 20, atoms and photons. And I guess what we're going to do here is we're going to talk about photons and atoms and how these things interact. But we're going to start this with sort of a Bohr model of the atom. So you remember the Bohr model where you have a proton with Z, that should be a capital Z charge, so it's a plus Z. And that's, so we have our nucleus with the Z protons is how it should be. And then you'll have the Z electrons zipping about in their orbits. You'll have one going this way, and then you'll have another one going the opposite direction, basically, to get opposite magnetic moment, so they cancel. And for purposes of this discussion, we're only going to look at the S states, so then there'll be another S state here, and so forth. So we'll ignore P and D and higher states, because that's just making things harder for no particular reason, right? So you don't want to randomly make problems there. So this basically has orbits, and each orbit has two different states. In the real world, they have additional different states, or actually it's really weird in the real world. So we'll ignore the real world because the real world is weird. All right, that's all we're going to do. So this is going to be 0. I'm going to pretend like this is our nucleus. We can just look at these different energy levels, right? So this is our energy here, as sort of little spots for the electrons to live, right? And then keep it getting closer and closer together, but there are an infinite number of them, so that they're really, really dense up here, right? But this is a very small difference in energy, so it's actually really hard to get into those really high level states because they get pretty fine, so you have to have extremely fine control of the energy for things to get there. And we'll label this as the ground state. We usually call that 1. And then we have 2 is the next first excited state. The second excited state is 3, 4, and so on. So this is number n, the energy level. This guy is 1, right? This is the ground state. This guy is 2, and this guy is 3. And they just get higher and higher and higher. So that's sort of the old Bohr model. The electron, where you have an orbiting thing, sort of like a solar system. So it's that solar system model of the atom. And we don't really believe that anymore, but it's a pretty good model for doing a lot of things. In fact, it gave us a really coherent idea about how what's going on here in switches. So it's the first thing that told us, and we're going to call this up and this down, right? One's going clockwise and one's going counterclockwise. Basically just that we fill up our electrons in order, like that, right? So we fill up our electrons in this nice canonical order, and we can talk about how many electrons are in each spot and things like that. And that's sort of what the Bohr model gives us. It also tells us that you have to have these specific energies. And it gives us a little bit of idea about what their electrons are doing. It's not really what they're doing, because electrons are weird and fuzzy things. And we don't want to talk too much about their weird fuzziness. So these energy levels here are given by E sub n. So if n equals 1, that is going to be the energy. Now these are all negative because we're calling this the zero of energy. This is the last, the infinite excited state. If you push this guy up over here, then he's going to become a conducting electron. All right. So we're going, everything below that zero is our energy, and that is z squared. So that, remember, that's our atomic number for our atom, over n squared, and that's the energy level. So the second energy level has 1/4 the energy as the the ground state. So the first excited state has 1/4, the third has 1/9, the fourth has 1/16, and so on. So the amount of energy just keeps reducing as you get higher and higher and higher, closer and closer and closer to zero. But you can see that you never get to zero because it's always, n is always less than infinity. It's a real number. This is called the Rydberg constant here. Oops. Close. And that number is, RE is equal to, I don't know this one off the top of my head. It's 13.6 electron volts, but we'll use joules, 2.18 to the minus 18 joules. Okay, so that's not a lot of energy. You don't expect it to be a lot of energy because it's just one little electron and one little atom, right? So you don't expect to have all sorts of stuff going on, all sorts of energies that we have to worry about. So that's our model, is that an atom is composed of Z protons plus some neutrons in the nucleus, but we don't really care about them for this analysis. And an equal number of electrons. All right. So that's the first thing. Second thing is here and here. Each electron inhabits or sits in an energy level all its own. And let's see, 2 electrons are allowed in each level. So that's this thing here. We have the spin up, spin down, going clockwise or counterclockwise. That's the two different electrons, and each one is in one of these specified levels. So that's pretty much our model of the atom that we're going to use. And next I'm going to talk about how that model is used to describe how interactions occur between the atom and the electric field. All right? Bye.